this is my Physics 2212 Lab 3 magnetic field of a bar magnet. So our purpose is to observe the distance dependence of the magnetic field of a bar magnet. We're going to measure the magnetic field using Biot-Savart law. We're going to use glow strip to simulate that magnetic field, and we're going to compare it to the measured magnetic field. So previous results is we have our magnetic dipole moment over here. We have the value of n, the measured magnetic field, and the simulated magnetic field. So some fundamental principles is the Biot-Savart law, which can be seen right here in the distance dependence equation, which is over here, and we're going to use this information to find k and n. So the system is going to be the bar magnet, and the surrounding is going to be everything else. So you're going to pinpoint the location of the magnetic sphere by sliding the phone perpendicular to the ruler, vertically and horizontally, so you can find the distance at which the magnetic field is the strongest, and that can be seen in this picture. And the on-axis magnetic field was found by finding the on-axis distance from the bar magnet to the magnetosphere, or magnetometer, for different magnetic field values. And the off-axis magnetic field was found by finding the distance where the magnetic field was 100. And this distance is then applied in the y direction, and that makes the magnetic field at the point d perp, and 0. And that can be seen in this picture. So here's the data when we took it at 20, 70, 120, 170, and 220. That data was put into the graph. So here you have the equation where n, this is going to be the value of n, and you have the value of ln of k. And then this off-axis field will be used to compare the value of 6.36 times 10 to the negative 5. So when the magnetometer is far away from the magnet, it measures non-zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measure x component of the magnetic field increases. So the calculations, this was the equation as found earlier. The slope is going to be negative 3.0429, which is the n value. And then ln of k is going to be negative 14.632. If you do e raised to that, that's how you get k. And you're going to plug all the information to the Biot-Savart equation to find mu, and that's going to be 2.21. So this is a computational model. So here we have that 2.21 as our mu, and we're going to multiply that by mu hat. And then here we're going to create a function for the magnetic field. So we have r mag, and we're going to take r hat by taking the components divided by r mag. And this is the Biot-Savart equation, so we're going to plug all that information in there. So then we scaled the arrow and found distance so we can make it easier to see on the graph. And here we have the different axes. We have 2 on-axis and then 4 perpendicular. So that can be seen here based off the x, y, and z components. And then we're going to draw arrows for each of these. So for the r-axis one, it's going to be obs axis 1. And then you're going to take that dipole B from earlier and plug that in. And you're going to make your axis, your B scale times that axis. And you're going to do that again for the second obs axis, the on axis. And then you have the 4 perpendicular, and you're going to pretty much do the same thing, except you're going to plug in the perpendicular axes. And your d perp was, my d perp was measured to be 0.166. So we found d by taking that and taking the square root of 2, or multiplying it by the square root of 2. And then we're going to observe the location of 45 degrees. And all this was printed out so you can see this. So you have your b axes and your b perps right here, your d, and then the b at 45 degrees at distance d is right over here. So as the distance between the magnetometer and magnet decrease, the magnitude of the magnetic field increases. So as we said before, this is mu, and then the measured magnetic field is 6.36 times 10 to the negative 5, and the simulated one is 2.7 times 10 to the negative 5. Some possible sources of error is that other magnetic fields from the surrounding could have distorted the measurements. The movement of the phone during the measurement may have caused some error. The surface was probably not completely flat. There was probably some measurement error with the magnetometer, and the measurement error with the distance between the magnetometer and the magnet. So what if you hadn't oriented your experiment to compensate for magnetic north? The x and y components of the magnetic field would be different because the magnetic north would contribute to the magnetic field measurements. There would be some inaccuracy in the results, as it's difficult to isolate and study the magnetic field produced by only the bar magnet. What if you were to stick 2 identical magnets together and run the experiment again? So the direction of the magnetic field would stay the same. However, the measurement of the magnetic field would increase because there's a greater magnetic force. Okay, thank you.